What's up, guys, and welcome back. So let's continue now with the data analysis part, where we try to pick or select the best algorithm, the best techniques that we can use so that we build or we develop the most accurate model. So this is all about the data analysis part, where we are going to go through various steps to select the best. Okay, so the first thing is that we import the necessary libraries. So these are the NumPy, the pandas, matplotlib. Then we also import the PyMongo as well as the Mongo client, so that we are able to read the data that we saved in the MongoDB server. So again, I think you remember this. So where you connect the MongoDB database using the Mongo library in Python. So again, it creates the client, the Mongo client. Then I think you remember this link. This is the link that this one here. Okay, so we can just use the same. So you pass in the link again. This is the password. This for my database. So this is the database. So don't use my password for this. You can just create yours. Okay. Then when you print the client, you can see this is some metadata about that. Then you can establish a connection to the MongoDB cluster. Again, this is all about this. When you establish that connection, then you select the Betty experiments database that we created. So remember, we created let's go to our database. So browse collections, you can see we had a database with the name Betty experiment. So this is the database. So you select the database that you want to query, then select the collection itself. So this is the collection name. Then from here you convert the entire this one Betty rule as a collection name to a pandas data frame. Okay. So the lists, so this function list collection, this retrieves all documents from the collection and converts them into a list. Then from here you convert this into a data frame, so that we are able to use you're able to do the analysis as a pandas data frame. Okay, so with the df.head you are able to print the first 5 rows of the data frame. So this is how you import, or this is how you can query the MongoDB database and import the data. As you can see, it's not that much complicated. It's just something that you can handle. Then it's just a simple code. So from technically, it's just, this is the entire code from here up to here. You can just see it's just about 1, 2, 3, 4 lines of code. Okay, so now we have our data. So df.info, just to have a quick glance overview of our data, you can see we have a total of 15,064 entries, the number of rows, a total of 10 columns. You can see rule is now, RUL is now the target column. Okay, so I'm going to drop this ID column. So this is just something like alphanumeric key to denote the different columns in the data. Okay, so I'm just going to drop this because it is irrelevant in our data analysis. So I'm just dropping that. Then you can do the data.describe to get the statistical information about your data, about the count, the mean, standard deviation, the percentiles, maximum value as well as the minimum value. So you can do this to see about gain more statistical information about your data. So again, we can plot histograms to determine the data distribution. So for the histogram, selecting the numeric columns, then I've defined the grid layout, so how the charts will appear. Then I'm using the flatten, so that the NumPy arrays, to flatten the NumPy arrays. Then you can use the for loop to just plot the histograms. Then we are going to hide the empty subplots. We don't want, in case of space, we don't want an empty chart. Then we can plot this. So this is the chart, and you can see how the distribution of data in the respective columns. Okay, so we can plot a box plot to check for outliers. So these are just techniques that you can use to see to gauge the suitability of your data. So again, select the numeric columns, the grid, then you plot. Then when you execute this, you can see this is how the you can see from the box plot, you can see that our data contains a lot of outliers. So this is one thing that we need to solve before we train our model. So for that, you can also plot the correlation, the features, plot a correlation matrix to see how the features are correlating with the target variable. So correlation matrix, this is the correlation matrix. You can see this is the diagonal. You can see how the different features are correlating with the target variable. So before we do any data cleaning steps, then you can see that some of the columns, for example, the max 0.75, the maximum voltage discharge, you can see this one is one that is almost having a higher correlation with the target variable. This one, the discharge time, the decrement from 3.6 to 3.4 voltage in seconds. Then you can see this one. I can use let's create a marker that let me use a marker. So you can see that for this, you can see that they are not highly correlated with our target variable. So this is the target variable. You can see how the different columns are correlating with the target variable. So you can see there's no much correlation between the target variable and no, this one. I'm sorry. Our target variable, I think, is this one. Our target variable rule is our target variable. So our target variable not finding the cursor. Where is the cursor? Just remove it anyway. So then, so earlier on we saw that we were having a lot of outliers. So let's start dealing with the outliers. So I found two ways to deal with the outliers. One was all about looking for removing outliers from the individual column. Another one is all about trying to remove the outliers, but from the entire data frame. So we are going to see removing outliers from the entire data frame and removing outliers from the individual column. So we're trying we will query both to see which one works best for us. So the approach for this, the targeted approach, this allows you to address the outlier specific for each column now without affecting the other variables. So for example, if we had only one column that is having outliers, then we are just going to target only that column. Then from there, we are able to reduce a bias by only focusing on the individual columns. But the downside for using this technique is that it's more complex. Does not consider the potential relationship between variables, which could also be important in outlier detection. So these are some of the cons when using this approach. So you can also use this when trying to consider using the removal of outliers from the individual columns. So if you have a large number of columns, then you can consider it. If you want to preserve as much data as possible, then you can use it. Then you suspect that the outliers are specific to certain features. So for example, you can see rule is our target column. So for example, you can see the cycle index. It does not, technically, it does not contain outliers. So, but a column such as the box plot for discharge time in second, you can see the other columns are having outliers. So if you only want to deal with outliers from the specific columns, then this is the best technique that you can use. So this is what we applying here. So we select the columns, then store the original number of rows, original number of rows. So this one. Then we calculate the z-score. So when it comes to removal of the outliers, then I'm using the z-score. So I can just do away with this at the moment and store the filtered data frame in df.filtered. So this one here. Then we can display the number of rows before and after filtering. So originally we had a total of 15,064 number as the number of rows. Then after doing the outlier removal for the individual columns, then this is what we are remaining with. Okay. When removing the same for the entire data frame, so just remember everything until this point is just the same. Just using the same thing, only that we are trying to change the process of dealing with the outliers. So for this one, we are removing from the entire data frame. So again, you can read through, you can see the pros of using this as well as the disadvantages of using such a method when removing the outliers. Also the what to consider if you're going to be applying the same technique when removing these outliers. So we are just doing the same thing, but I think this one is where the code is a little bit different. Then after that, you can see that we are trying to display the number of rows before and after filtering. Again, you can see the original number of rows, 15,064. Then we are remaining with about 14,721 after filtering. And for this one is 14,513. So we ended up removing a lot of rows when dealing with the individual columns than when we are removing outliers from the entire data frame. Okay. So let's plot again let's plot again or what we can do. Let's something like this screen. So earlier on, before removal of outliers, then everything is the same. So you can see there is a slight improvement in terms of data distribution. So for the cycle index, you can see just remaining the same. This histogram, you can see we are trying to form that normal curve. Then histogram for decrement, again, you can see again that a normal curve is almost forming, as well as for the rest of the columns. The one column that I think that one is that normal curve is almost being perfect. You can see is the charging time second. You can see we have a slight improvement before and after removing the outliers. So this one is after we have removed the outliers. This one is before we have removed the outliers. So when we compare, this is from the entire data frame. This is from the individual columns. So when we compare that, again, you can see that when we remove from the entire data frame, I think it's working best. Visually, you can see it's working best when we just remove from the individual columns. So you can see, for example, this is the charging time in seconds from the entire data frame, and this one is from let me see if we can use marker. So use this. So you can see, for example, this column and this one here. So you can see when we remove from the individual columns, this one is for the entire data frame. You can see it is working best if we remove from here, because you can see that curve is almost forming. Again, for this one here, almost the same. Okay, also don't know. Okay. Yes. Okay. So in terms of feature elimination, so we are going to see if you can eliminate some features. So earlier on, we used the correlation, and you can see how the features were correlating with the target variable. So after removing the outliers, we can see that there is a slight improvement in how the different features are now correlating with the target variables. Okay, so this one is the previous chart, and this one is the after removing the outliers. So you can see we have after removing the outliers, we have increased the correlation between the target variable and the other features. So technically, when trying to build a model, we are going to be it's going to perform well when we are trying to fit that line in our data points. Okay, so this one is for the individual columns. Also, when we do that for the entire data frame, you can see also this some difference. So you can see for the individual columns, for example, let's compare this column, discharge time in seconds. It's about -97. This one is about -0.77. So it's highly correlated when we remove outliers from the individual columns than when we remove from the entire data frame. Okay, so from here, let's build our model. So we can import the different regression. So this is a regression problem. Then preprocessing the different preprocessing techniques, the standard scalar, the min-max scalar, the train test split. And also in terms of evaluation, these are the metrics that we are going to be using for evaluation, including the mean absolute error, the mean squared error, and the R-squared score. You can also determine which algorithm is faster in terms of training as well as doing the predictions. Okay, so after this, we define the features and the target variable. So we drop the missing values in our data frame. Then these are our features. Every other column except the column rule. Then the target variable is this one. Then you can do a training set and the testing set split. For scalar, I'm using the min-max scalar. So we fit the scalar onto our training data set, and then we just use the same scalar, but we transform. Instead of fitting and transforming, we just transform the testing data. So after that, we can now define the models that we are going to be using under this analysis. So we have the decision tree, extra trees, random forest, gradient boosting, k nearest neighbors are regressor. We have the cut boost all the way until the XG boost regressor. So these are the different algorithms that we are going to compare and see which one is working best. Then we can initialize a dictionary to store the results. So for the model, the mean absolute error, the mean squared error, the root mean squared error, the mean absolute percent error, as well as the R-squared score. Then we can the training time for both training and the prediction time. Okay, so when we execute this, so we create a loop for doing the training, then for evaluation, then for storing our results and printing out the data frame. So when you execute this, so you can see the model and the different evaluation metrics, as well as the training and the prediction times. So the same thing is also happening when we are dealing with the entire data frame. So we can just do a comparison. So for the comparison, you can see, let's see how for both how our model is fitting. So I'm just going to use the R-squared score to compare. No, let's use the mean absolute error. Technically, we are not getting, we are almost getting the same values. They are not way apart significantly. So for example, if you see the decision tree 2.06, this is about 2.2, 21.94, this is 25, 4.68, this one is 5.08, this is 1.08, 1.2606, 999.99. So when you compare the two, you can see that even though these the results of the evaluation are almost similar, you can see they are better when we remove the outliers from the individual columns than from the entire data frame. Okay, so when it comes to the training time, again, 0.16, 0.13, 0.42, 0.48. When it comes to training time, I think for the training times, training happened faster from the analysis where we removed outliers from the entire data frame. Okay, so we can just compare those and see. So we are going to plot some charts for this. So when we for this one, let me go to a full screen. So this is a chart showing, so this chart is just a representation of this. So we are trying to compare the different algorithms with the different evaluation metrics that we selected to try to visualize and see which algorithm is performing better. So if you want to compare the mean absolute error, so you can just click on the other variables and they will sort of be removed from the chart. So you're only remaining with the mean absolute error as an evaluation metric, and you can visually compare the different algorithms. For the mean absolute error, you want to keep this value very small. So you can see for the x-axis, it's doing better in this. For the mean squared error, you can see again x-axis is performing better, followed by the xg boost. I think so. It's about 13.59. This one is about random forest, about 12. So x-axis, random forest, and then the xg boost. For the root mean squared error, you can see the x-axis. So you can also do this comparison and see mean absolute error. So you can see how the different algorithms are performing. Okay, so if I remove this, you can see now mean absolute error, root mean squared error, mean absolute percent error. So you can see how the different algorithms are performing. So in terms of training times, so you want to select a model that has the least training time as well as the prediction time. So for the effect of the latency, when the user inputs data to the when a user wants to do the prediction, then it's better if they get the predictions as quickly as possible. So you need a model that has the shortest training time as well as the prediction time. So for the training time, we can see decision tree, LGB, mregressor, XGBoost. Those are the algorithms with almost the least training time. And for the prediction time, we can see decision tree as the least. XG regressor, and all that. Okay, so we can plot the scatter plot. So earlier on we saw that our features were highly correlated to the target variable. So we do expect such. So they were almost 0.99. So we do expect this. Okay. So we can use again the residual plots in this analysis to try to again to select the best algorithm. So residual plot. A residual plot is a graphical representation of the residuals. Now this is the difference between the observed values and the predicted values, and they are plotted against the predicted values. So what does the residual plot tell us? Okay, so pattern detection. Ideally, the residual should be randomly scattered around the horizontal axis. So as you can see here, the residual should be scattered along the horizontal axis. This indicates that the model has captured all the systematic information and the remaining noise is random. Okay, so for the residual plot, what you do expect, you should have a constant spread along that horizontal axis. For the changing spread, if the residual fan out or form a funnel type of shape. So funnel type of shape is something like this. For example, if your residual plot forms something like this, or something like this along the horizontal axis. So remember, this should be the horizontal axis where the residual equals to 0. Okay. So this one here. So x is equals to 0. So if there is a funnel, so constant spread, if the residual have a constant spread around the horizontal axis across all levels of the predicted values, it indicates homoscedasticity. This means that the variance of the residual is constant and the model's predictions are equally reliable across a range of data. So you need to have a constant spread other than having a funnel type shape of a spread, okay, to ensure you are able to achieve this. Also, the model fits centered around 0. Residual should be centered, indicating that the model predictions are on average accurate. Systematic deviations from 0 can indicate a bias. So in terms of outliers, also the residual plots can help us to identify outliers. So points that are linear, points that lie far from the rest of the residuals suggest that the model performs poorly. So you need to have this residual should be very close to your horizontal axis, where the residual equals to 0. Okay. So from this, the gradient boost, you can see there's something like a pattern that is being formed. So it won't be the best one. So the KNN is trying to achieve almost a perfect residual, but we do have these residuals that are spanning out. You can see negative 150, 100. You can see that difference is quite huge. For example, if you compare, for example, the KNN as well as the decision tree, you can see this one is about a negative 40, about 30. This one is about 100, 150. So you can see we do have residuals, these values that are way far from the horizontal axis where the residuals are 0. The LGBM, you can see, is quite performing well between -20 and 20. So that's okay. For the XGB, again, -20 and 20, performing also well. This for the cut boost is about -40 and 30, Okay, so we expect to be in that range. So if we expect that our residuals to be between 40 and minus 40, then what we can do, let's try to cancel out the algorithms that, so for the K and N, we are going to consider it as not an option, as well as for the gradient boost. This we are going to eliminate this. So we are remaining with the decision tree, extra trees, random forest, LGBM regressor. We also have, there's something that I'm finding it hard to, I think I've managed. So we have removed, so let's do that again. Try to do this one. Then try to change the color. Let's use red. So we have removed the K and N as well as the gradient boosting. Okay. Earlier on, based on the training times, what we can also remove, let's look at this guys. So for example, go away with this, then I can just I think this one is okay. So when we look at the training times, you can see the extra trees and the random forest. We are having higher training times. Okay, so technically, I want we can eliminate these ones, these two, with the reason that they are taking a lot of time to make the predictions. So, for example, as you can see, we're only having 15,000 entries. So if we have more entries than that, then it might take a lot of time to train our model using the extra trees and the random forest, even though they are they're performing better in terms of when you compare the evaluation metrics. Okay, so I'm going to do away with those. Then so when we come back to this point, so what we can do, we can say that we are doing away with the extra trees and the random forest because of the training time. So for real-time predictions, these ones won't suit us for the real-time predictions. But for if you're doing something like a batch predictions, then you might select these ones. Okay. Then we said for the gradient boosting and also the K and N. So these ones I have already explained as to why we are dropping this. For the LGBM, decision tree, LGBM, cut boost, and XGB. So let's see how this will perform when we look at the kernel density plot, KDE plots. So the KDE plots are just plots or an extension of this of the residual plots. So this is just an extension for that, in that we are trying to plot those the KDE plots. So the KDE plots, I found them more visually appropriate to use than the residual plots. Okay, so the KDE plots in regression analysis is used to visualize the distribution of the residuals, which are the difference between the observed values. So those are the actual values and the predicted values from the regression model. Okay. So what does the KDE plot tell us? So residual distribution. So this shows how the residuals are distributed across the different values. Ideally, the residuals should be symmetrically distributed around 0. So something like this, but in terms of the KDE plot, not a scatter plot. Okay, so this one can be a scatter. This is a scatter plot, I think. So the residual plot is just something like a scatter plot. Yeah. So the presence of bias, if the KDE plot shows that the residuals are skewed on one side, so it suggests that the model might be biased in its predictions. So those are the things that we need to consider. Then we can also consider the heteroscedasticity. A uniform spread of residual suggests this term is very hard to read, homoscedasticity. Okay, so a uniform spread of residuals suggests homoscedasticity, meaning that the variance of the residuals is constant across all levels of predicted values. Okay, if the spread of the residual changes, e.g., fans out or narrows down, it indicates heteroscedasticity, which can be a problem for certain types of regressions. So we need to consider that. Also, we are able to see or denote the outliers from the KDE plots. Okay? So what is the ideal? It should be centered around 0. So that should be the ideal KDE plot for a model that regression model that regression algorithm that we need to select. And the symmetric shape, the plot should be symmetrical, suggesting that the model errors are equally likely to be positive or negative, smooth and single. Then it should be a smooth and a single peak. Okay, peak around 0 indicating normal distribution. So essentially, with this KDE plot, we are trying to find the one that has the best smooth normal curve, something like that. Okay, so again here we are going to compare the different KDE plots for the different algorithms. So this one is for the kernel density. So let's use a pen, so I can just go with that. And here, so let's see again, we are building a model for real-time prediction. So for that reason, we said extra trees and the random forest, we are going to do away with those. For the gradient boosting, as well as the KNN regressor, we saw that KNN regressor has a lot of outliers, despite us removing those outliers. Then for the gradient boosting, there was still some pattern from the scattered approach. So again, you can see we have these effects. We need to have a smooth curve. Okay, so for the LGBM regressor, we can see we are having some the smooth curve is not panning out smoothly, okay, as it tends to 0. So for that reason, again, I'll do away with this. The cut boost, again, cut boost -20, something like so what we are remaining with is the cut boost, decision tree, as well as the XGB regressor. So I think the decision tree is working quite well, but even though we are not getting, you can see some issues here. Then I think cut boost and XG, so cut boosts and the XGB regressor. So you can select, I think from here, if you select the decision tree, the cut boost, and maybe the decision tree, the XG boost, and the cut boost, I think will be better. So so we have the decision tree, cut boost, and the XG boost. So let's compare those in terms of training and the testing time. So XG, this one is 0.16. Training time, this is 0.23. For the cut boost, this one is 10. Again, this one you can just do away. It's taking a lot of time. So decision tree and the XG boost. For this case, I'll go with the XG boost. So in the previous video, while we are doing I think in the previous, when we were doing the electricity bill prediction, when we are developing that model, we used the decision tree. So for this case, I'm going to use the XG boost regressor. So let's try a different algorithm, okay, for our model. So that's it for this analysis. We saw that how we can do data analysis, the different steps that we can employ in our data analysis to try to clean our data, to make sure that our data, we are going to get better scores when we try to build the model. So there are different data analysis steps that we have tackled in this analysis. You can apply this and several other techniques to try to clean your data, because when you are trying to build this model, they feed off of data. So for this case, we tried to explore a data-centric approach. So we try to clean our data as much as possible, remove the outliers. In most cases here, we tried that by just trying to remove the outliers. Then we tried different algorithms, and we saw how they are performing. Then we tried to eliminate those the different algorithms. We tried to eliminate basing on the different basing on what we are required for this, what is required for this model. Okay, so we saw how the reason as to why we did not select the extra trees as well as the random forest, even though they were performing better. For that reason, we say that we wanted to build or develop a model that can do a real-time prediction. So for the real-time predictions, you need results quite faster, and that when using those, it might cause some lagging or higher latency. Okay, so that's all about the data analysis. So the different steps that we have applied under this analysis. So when we are developing our model, during the data preparation, the steps that we have developed under this are the same steps that we are going to be using under the data transformation. So you can see how we can apply those steps and the sequence that we will be using while applying those steps in during the data preprocessing step. Okay. So with all that said, we have now reached the end of the data analysis. Now we have selected the algorithm, the algorithm that we will be using, and we have noted the different steps. The next step is all about now starting the development phase. Okay, that will be the next step after this. Okay, once again, thank you for your time. Thank you for finding time to watch these videos. So before we end this session, again, please consider subscribing to the channel. We're welcoming you to this wonderful community. Hit that notification bell so that you never miss any of our video updates. You can also share this with your friends. Sharing is caring. Let them also learn the different techniques that you have learned from this. Okay, so share with them. You can also comment, because We very much like hearing from you. Once again, thank you for your time. See you in the next one.